Hello, my name is Rares-Darius Buhai, and I am presenting the paper Approaching the Threshold for Semi-Random Planted Clique, which is joint work with Pravesh Kothari and David Steurer. Let's start with the planted clique problem, where the idea is that you have a random graph, and you select a subset of k vertices, and you put a clique on them. So we'll depict that as follows. You have on the left hand side k vertices S star, and on the right hand side n minus k vertices v minus S star. And you also have edges going between S star and v minus S star. So any graph can be depicted as follows. So in this model, we assume that S star is a k clique, so a clique of size k. And for all the other edges, both those between S star and v minus S star and those within v minus S star, we assume that they're random, that they are selected independently with probability half. And then the goal in this model is to recover the planted clique S star. And it turns out that how difficult this is depends on the size of the planted clique, on the size of k. So specifically, for k less than 2 log n, it's actually known that it's impossible to solve this problem, because in the random portion of the graph, with high probability, you'll have a clique of size approximately 2 log n. So then it's impossible to distinguish S star from this clique that just appears in the random part of the graph. And conversely, for k larger than 2 log n, it's possible, information theoretically, to find the planted clique, because with high probability, the planted clique is the maximum clique. Okay, what about polynomial time algorithms? So when k is at least root n log n, it's known that just taking the k vertices with the highest degree gives you the planted clique with high probability. And when k is at least some constant times root n without other log factors, there's another algorithm that takes basically the second eigenvector of the adjacency matrix and rounds it. So when k is at least some constant times root n, we know that the problem is solvable in polynomial time. So what happens when k is between 2 log n and root n? Well, it's proved that it's hard for sum of squares programs to solve the problem in this regime. So sum of squares programs are a class of convex programs which capture almost all average case algorithms and almost all estimation algorithms that we have so far. So the fact that this cannot be solved in polynomial time by sum of squares programs is taken as evidence that the problem is actually hard. Okay, but for k at least root n, you can solve the problem. So let's take the positive here, because you cannot do this in a worst case graph where the problem is just NP hard. So then it's interesting to try to understand if we can achieve similar guarantees in a graph, in a model that's more adversarial, so without all this randomness. Like how close can we come to a worst case graph while still being able to recover some planted cliques? And the model that we're going to study is the semi-random planted clique model introduced by Feige and Killian. So the model looks as follows. You still have k vertices on the left and then minus k on the right. S star is a k clique. The edges between S star and v minus S star are generated randomly, but then an adversary can remove any subset of them. And for v minus S star, we assume that this subgraph is completely adversarial. So the adversary can select it arbitrarily, and it can select it adaptively after seeing the randomness of the edges between S star and v minus S star. So this model comes close to a worst case model in the sense that the only thing that's not worst case is the cut between S star and v minus S star. So what's the goal in this model? Because it's actually impossible to recover S star. Why? Because in v minus S star, the adversary could put a k clique and another k clique with random cuts between them. So then it's impossible to tell which is S star and which is one of these cliques that the adversary put. So then our goal will be to recover a list of O of n over k cliques that includes the planted clique S star. So why n over k? Well, the adversary could simulate this up to n over k times, like put up to n over k cliques such that all the cuts between them are random. So we cannot hope for anything better than n over k, and we'll see that it's possible to get n over k. Okay, so let's see what is known for this problem. So for k at most root n, it's actually known that this is impossible information theoretically. It's impossible to recover a small list that includes the true clique. And this has been proved by Steinhardt. So note that this is different from the planted clique, where the impossibility is at log n. Now for polynomial time algorithms, when k is at least n to the 2/3 times some log factors, it can be solved by a semi-definite program given by Charikar, Steinhardt, and Valiant. And then this was improved by Mackenzie, Mehta, and Trevisan to n to the 2/3 without any log factors, also based on a semi-definite program. So up to our result, it was known that you can do this in polynomial time when k is at least n to the 2/3. And it was left as an open question by Steinhardt and Feige, what happens between root n and n to the 2/3. And they conjectured that maybe it should be possible to have polynomial algorithms that solve the problem at root n or close to root n. So in our paper, we almost answered this question by giving an algorithm that approaches root n. So basically, we give an algorithm that works when k is at least n to the 1/2 plus 1 over t in time n to the O of t. So as you increase t, you should think of t as a large constant. As you increase it, you get closer and closer to n to the 1/2. So for t 100, you get k at least n to the 1/2 plus 1 over 100 in polynomial time, like n to the O of 100. Yeah, so this is our result. And our theorem statement looks like this. For any t a natural number, we give an algorithm that runs in time n to the O of t, such that if k is at least n to the 1/2 plus 1 over t, it outputs with high probability a list of at most 1 plus little o of 1 times n over k cliques, such that S star is in the list. So let's discuss now how we can achieve these guarantees. And I'm going to start with an inefficient algorithm. So let's assume for now, and for the rest of the talk, that there are no adversarial deletions. So let's assume that the edges between S star and V minus S star are truly random. And it turns out that for our algorithm, it's easy to put this assumption back in at the end. So I want to emphasize that it's not clear what an inefficient algorithm should be. Because if you just try to output all the k cliques, there can be exponentially many, so we are not going to return a small list. And remember that we want a list of size at most n over k. And this can happen because V minus S star, for example, could be a complete graph, so then it has roughly n choose k cliques. So the main claim that helps us is the following, observed by Steinhardt, that with high probability, S star intersects every other k clique in the graph in at most log n vertices. So if you have, for example, this red circle, which is a k clique, you know, some part of it intersects S star, and this claim says that this intersection has size at most log n. And this is roughly because if you have such a clique, then there must be a lot of connections between the left-hand side and the right-hand side of this red clique. So in the cut between S star and V minus S star, you need to have some highly structured set of edges, but we assume that these edges are random, so this cannot really happen. The second claim that will help us is that when k is at least root n times L, we have that any list of k cliques such that each to intersect in at most L vertices has size at most n over k. So what this says is that if you have k cliques that are large enough, and if their intersection is small enough, if they have small intersection, then basically you cannot have too many of them. Because if you just try to put them more and more, like, they quickly fill up the graph. So actually you can have only kind of the optimal amount of them, which is O of n over k. So these two claims are enough to give us an algorithm that works when k is at least root n log n, which is better than what our algorithm achieves. So the algorithm is simply to output all the k cliques that intersect every other k clique in at most log n vertices. So note that this outputs S star, because S star intersects every other k clique in at most log n vertices. And now how many cliques does it output? Well, k is at least root n log n, and the intersection of every clique in the output is at most log n. So by the second claim, that there can be at most n over k such k cliques. So the size of the output is at most n over k, or O of n over k, so this solves the problem. So now our goal is to get somehow an efficient algorithm. And I want you to notice that the key structural property that we used so far was that S star intersects every other k clique in at most L vertices, where so far we use L equals log n by Steinhardt's claim. It turns out that if you can certify such a statement in time n to the t, there is a general machinery based on a sum of squares program of size n to the t that gives you an algorithm that runs in time n to the O of t and solves the problem, like gives you a list, a small list, whenever k is at least root n times L. So this general machinery to obtain a list from certificates of small intersections has appeared in various previous papers, mostly in mostly for estimation problems. So I cite here one example for linear regression with many outliers. And it turns out that we can adapt this kind of machinery and make it work for our problem of finding planted cliques. And then what we do is that we give a certificate. We show that we can certify in time n to the O of t that L is at most n to the 1 over t. Which, if you plug it into the right-hand side, you get that this gives an algorithm that runs in time n to the O of t and solves the problem whenever k is at least n to the 1/2 plus 1 over t. So let's focus now on the certification problem. How can you certify that S star intersects all the other k cliques in at most L vertices? So what does this even mean? For the certification task, we assume that S star is known, and we just want to prove to someone efficiently, based on explicit properties of the graph, the fact that every other k clique intersects it in at most L vertices. So let's observe a few things. First of all, the cut between S star and V minus S star gives a random k by n minus k bipartite graph. So here I'm ignoring the connections within S star and within V minus S star, and I'm just looking at edges going between them, and then this is a random bipartite graph because all these edges are random. Then, if you have a k clique that intersects S star in L vertices, this means that the cut contains an L by k minus L biclique. So what I mean by this? Suppose that you have like a 5 clique that has 2 vertices in S star and 3 in V minus S star as depicted. Then all of these must be connected to each other because it's a clique. So this structure, where every node on the left is connected to every node on the right, we call this a 2 by 3 biclique. So in general, if you have a k clique that intersects S star in L vertices, this is going to give you an L by k minus L biclique. Then, it actually suffices to certify that a random k by n minus k bipartite graph does not contain any L by k minus L bicliques, because this implies that any intersection of a clique with S star has size less than L. So from now on, we're going to focus on this certification task. And for simplicity, we're going to show that in a random k by n bipartite graph, there are no L by k bicliques. So instead of n minus k and k minus L, I'm going to work with n and k. So let's see how you can do this first with a simple certificate, a spectral certificate. So let B be the adjacency matrix of this random bipartite graph. So this is a k by n matrix where +1 represents that there is an edge and -1 that there isn't an edge. So B of ij is +1 if the ith node on the left is connected to the jth node on the right in the bipartite graph. Then as a certificate, I want to use the fact that the spectral norm of B is at most root n. So this actually holds with high probability for a random bipartite graph, and I'm claiming that this fact alone says something about bicliques, that you don't need to use anything else about the randomness except this spectral norm in order to get that, some bicliques cannot be too large. So let's see exactly what it gives. Let's assume that you have an L by k biclique in this random graph, bipartite graph. and let x and y be its indicators, x for the vertices on the left, y for those on the right. Then x transpose by is exactly equal to L times k, because these indicators, x transpose by, exactly select the edges in B that are part of the bi-clique. And all of these must be +1 because we have a bi-clique. Second of all, we have a trivial upper bound that x transpose by is at most norm of x, norm of y, norm of b. Norm of x, norm of y is at most root L times k. And the norm of b by the certificate is at most root n. So if you put these two together, you get that L is at most n over k, which means that the size of a bi-clique in a random bipartite graph is at most O of n over k by k, which also means that, going to the original problem, that the intersection of a k clique with S star has size at most n over k. So if you look at what algorithm this gives us, this gives you an algorithm when k is at least root n times root L. So when k is at most root n times root n over k. So if you simplify everything, you get that this works when k is at least n to the 2/3 times some log factors. And it's really interesting that this matches the up to log factors the previous results. Even though the previous results were not about spectral certificates and they were not about bi-cliques, it turns out that the spectral certificate kind of matches their power. So let's see now our certificate, which is higher degree and which is not spectral. We have again the adjacency matrix of the random bipartite graph. And we define a new matrix M of size k to the t times n, where each row of M is indexed by a set which represents rows of B. So each row of M is an element-wise product of some rows of B. And we do this for all sets of size at most t. So let's see this in a picture. Let's say that you have B1, B2, and B3 be the first 3 rows of B. Then M at the set 1, 2, 3 is just the element-wise product of these 3 rows. So you construct basically all such sets for all sets of size at most t. And our certificate is that for any 2 distinct rows of M, their inner product is at most root t times n. So you can verify that this holds with high probability in the random bipartite graph. And it's easy to see that for t equals 1, for example. When t equals 1, this just takes the inner product of 2 rows of B. So this ends up being exactly a sum of random plus minus 1 entries, a sum of n plus minus 1 random entries. So we know that this is at most of root n. Okay, so what does this strange certificate imply? Let's assume again that we have an L by K bi-clique and let x and y be its indicators in the matrix M. So y is +1 for the vertices on the right-hand side, and x is 1 for all the subsets of the left-hand side of the bi-clique. So then x transpose my is basically L to the t times k. L to the t because how many subsets are there of a set of L vertices? Because, you know, on the left-hand side you have L vertices in the bi-clique. Well, they're roughly L to the t. And now we also want an upper bound on this quantity. So by Cauchy-Schwarz, we have that this is at most norm of y times norm of x transpose m. In the next step, I'm going to expand the second term. So this is actually equal to summing over all sets S and T of size at most t that are in the left-hand side of the bi-clique, and taking the inner product of the respective rows of ms and mt. Now we can separate this into the part where S is equal to t and the part where S is different than t. And when S is different than t, we can actually use our certificate. Our certificate says exactly that this inner product is at most root t times n. So then overall, we bound the norm of y by root k. For the first sum, we have basically L to the t sets S that are in the bi-clique. And the norm of ms squared is exactly n, because ms is a vector of size n with plus minus 1 entries. And for the second sum, we have roughly L to the 2t pairs S and t. And for each of them, the inner product is at most root t times n. So now for a moment, I'm going to assume that L to the t is at most root n, which makes the first term in the sum dominate. And the next transpose my is at most root k times root L to the t times n. So if you combine this with the equality, you get that L to the t is at most n over k. So that L is at most n over k to the 1 over t. So that the size of a biclique is at most n over k to the 1 over t times k. So again, going back to the original problem, this says that any intersection with S star has size at most n over k to the 1 over t. So why was it okay here to assume that L to the t is less than root n in that step? Well, because we later showed that this implies that L to the t is even smaller, that it's smaller than n over k, and if we take k to be root n times n to the 1 over t, then we prove that it's even if you assume it's larger, it's still, you can still prove it's even smaller, so this works out. And now for an algorithm, this actually gives an algorithm when k is at least n to the 1/2 plus 1 over t. So this gives exactly the results that we want. So this basically completes our algorithm, this certificate. So I want to say just a few more things. First, about some lower bounds. We don't have any new lower bounds for the semi-random planted clique problem itself, but we have lower bounds for certifying that a random k by n bipartite graph does not contain L by k minus L bicliques. So first of all, we show that a basic SDP cannot certify that L is much smaller than n over k, which means that using this kind of certificate based on a basic SDP, you cannot solve the original problem for k much smaller than n to the 2/3. So again, the basic SDP somehow corresponds to the guarantees that the previous algorithms had of n to the 2/3. And we also have a low degree lower bound, which shows that you need polynomials of degree O of t if you want to certify a non-trivial L, a non-trivial bound, when k is at least n to the 1/2 plus 1 over t. So this somehow suggests that if you want to solve the problem for n to the 1/2 plus 1 over t, you need time complexity n to the t. Now, this is still a weak lower bound because we show this low degree lower bound for constant t. I mean, it only really makes sense here to talk about constant t mostly. And low degree lower bounds are considered in general credible once you show that you need degree larger than log n, which doesn't make sense here. So for us, we are just taking this as some weak evidence that the scaling that we have may be good because, you know, it corresponds to something if you do these so low degree calculations, but it's definitely not a rigorous proof. Okay, and I just want to talk a bit at the end about the result for general edge probabilities. So instead of saying that in the cut all the edges have probability half, you can say that they have probability p. And of most interest is the case when p is larger than 1/2, so when this cut is very dense. So in this case, we get that k, we can solve the problem in time n to the O of t when k is at least n to the 1/2 plus 1 over t divided by 1 over minus p to the t. So all I'm going to say here is that this improves upon the known algorithms whenever p is not super close to 1. So whenever p is at most 1 minus n to the minus 0.001, let's say. And that is because when p is much closer to 1, then this 1 of minus p to the t factor actually starts to be quite harmful. And I'm just going to say here that the conjecture threshold for general edge probability is root n times p over 1 minus p. So our dependence on 1 minus p to the t is, it's presumably not really optimal. So that's all I'm going to say about this general case. So I'm going to end my talk here, and thank you for listening.